PC Calculus, lesson 3.4, velocity and other rates of change. Fantastic amount in this section. I'm going to try and keep moving. Why did Newton study calculus? He was actually fascinated by the relation between displacement, where something is, velocity, how fast it's moving, and then acceleration, how fast it's changing its velocity. So we start with the displacement function. We're going to give it a different name real soon. We'll call it s of t. But we call it f of x here so we can relate it to our definition of the derivative. And if we take the displacement function and take the derivative, we get the IROC, instantaneous rate of change. The velocity. We'll also often just call it rate of change, but most of the time we call it velocity. So, for example, take a circle and take the derivative with respect to the radius. We've done this, it's just 2 pi r, which by the way is circumference, which I've had debates with several people about why that is. And we'll get to that another time, but that's the rate of change of a circle with respect to its radius. A lot of people get confused by the units. It is weird. Units are inches squared, because that's area per inch. Just makes no sense. But yeah, you're going to have to get used to it. So here's what we usually do, and if you're taking physics, you're probably all over this. Original displacement's s of t, the velocity is the derivative. The second derivative is the acceleration. Signs matter, so don't just toss them out. You have to be intelligent about how you use them. But for now, just remember signs matter. You can't just throw negatives out and say, yeah, who cares? If we are talking about English units, a body falls freely at, we'll call it g, negative 32 feet per second squared. If we're talking about metric, which I highly recommend everybody get used to because it's really very handy, we're looking at negative 9.8 meters per second squared. Here is the general formula, and once you know calculus, that's all you need for displacement. And this is the part due to gravity, and this is something in free fall, of course. It's just moving around. It's not being affected by gravity in terms of calculating it. This is due to the initial velocity. And this is due to initial displacement. Where did it start at? So, rock's thrown up in the air at initial speed. Wait a minute, speed. I should say velocity because speed is absolute value of velocity. So whenever we say, hey, what's the speed? We just stop, take absolute value of velocity. And otherwise, we just keep moving with velocity. It's thrown up with a positive 160 feet per second squared. So if we put that in here, it would be 1/2 g t squared. And this is feet, so I'm actually going to change that right away to 32 t squared. Going to ignore units for now. Don't forget to put them in. Minus 160 t, done. What happened to the third term, the initial displacement? It's thrown from the ground. Even though, if you think about it, it has to be thrown from 4 or 5 feet in the air where you let go of the rock. But for our purposes, we'll keep it there. So S of t equals 16 t squared minus 160 t. Acceleration of the rock, we can do this by going s double prime of t. And that would be, well, I don't like doing it that way. S prime of t is 32t minus 160, and s double prime of t equals 32 feet per second squared. But we don't have to do that. We know that this is a body in free fall, and that's the acceleration. It's nice to see that it works. What's the speed of the rocket at the top of its arc when you throw something up in the air? What's its speed right there? This is the key insight. You need to know that that is when the velocity equals 0. So we have S prime of t equals v of t equals 32t minus 160. When does that equal 0? So we do a little bit of math. Got my calculator handy. Solve it, and I get t equals 5 seconds. How high up does it go? Well, that's back to S of t, which I need to go look for. 16t squared minus 160t. Negative. Naughty, naughty, naughty. Negative. Negative. Negative 32. Naughty, naughty, naughty. Like I said, you got to watch out for the signs. Look at me forgetting to do so. What's the speed when it's 256 feet up? Well, 256 equals negative. So I never finished writing this. That's funny. Minus 160t. Negative 16t squared minus 160t. 16t squared plus 160t plus 256. Break it down to size a little bit. T squared plus 10t plus 16 equals 0. T plus 8. And I must have made a mistake somewhere. Oh, it's positive 160. Go back up and check. I have not given you a better way to say watch out for your signs. I hope that's it. Good. T minus 8, T minus 2. So we say it's at 256 feet, or no, this is how high up the rock goes. No, that's at 256, so I'm actually doing this problem wrong. I'm doing the second part first. At t equals 2 and at t equals 8. What's going on there is that the rock is going up in the air, and it passes 256 feet twice. Once on the way up, once on the way down. And if I know that, I can tell you that the rock hits its apex at 6. Pardon me, 5. Got to take the average. And then I can plug in 5. How high up does the rock go? But we already knew that from the previous section too. So S of 5 equals, doing this separately on a calculator, 400 feet. Need units for these. And that. So I've gone through this very quickly. We'll play with it a lot in class, but those are the basic ideas. AP exam loves this. They say, hey, particle moves along the line with position, blah, 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 blah. Find the displacement during the first 2 seconds. So you can graph this lots of different ways. We'll do it with parametric in a little bit. After 2 seconds, we're at -1, meaning it's moving backwards. Initially, this thing is going to be going backwards, and if we look at a number line, we'd say it's starting in the middle, it's going backwards. It might go further, might go less, and then who knows what it's going after that. Maybe it stops, goes back to the right. Who knows? So we'll see. Find the average velocity of the particle. T squared minus 4t plus 3. Average velocity. How far does it go in 4 seconds? How far does it go in 0 seconds? Velocity average is how far it went in 4 seconds, how far it went in 3 seconds. And notice I screwed this up before. It didn't start at 0. It really started at 3 and went down here to -1. Divided by total time for your average velocity for 4 seconds is 1. So we get units here. Meters per second. Instantaneous would be v of t, which is s prime of t, which is 2t minus 4. S prime of 4 would be 2 times 4 minus 4 would be 4 meters per second. So notice the big difference between average and regular. What's the acceleration? Take the second derivative of the placement, which in this case would be 2 meters per second squared. So there's a positive acceleration at all times. So where did it start? It started going left, but it's got a positive acceleration. So it started here at 3. I know it got to -1, maybe it went further, but it's going and it's going to eventually come whipping back the other way because it has a positive acceleration. So I just described the motion of the particle. When does it change directions? Well, at that instant right here, what's the velocity? That's right, it's 0. And my velocity function is 2t minus 4. Try and keep that up there because I can label that point now. 2t minus 4 equals 0. T equals 4 over 2 is at 2 seconds. Wait a minute, you said it's down to negative. Yeah, this is a displacement graph. This is S of t. So, can't quite remember. S of t equals t squared minus 4t plus 3. Don't want to screw that up. In addition to everything else I've screwed up here. S of 2 equals 2 squared minus 4 times 2 plus 3 equals 4 minus 8 plus 3 equals -1. So that is where this mins out at -1. Then it takes off and starts going positive. Want to see it? Me too. My computer's giving me a hard time here. So let's do it on the calculator. And we put it up on the line y equals 2 because it's hard to see when it's on the line y equals 0. So hopefully my calculator moves slow enough. I wanted it 2, but I also want to be able to see this thing. So I'm going to turn it into a dot. And yeah, have it trace something. And we'll graph. I gotta set the window. It's doing displacement, so I want it to go from an x min of -2 all the way up to, say, let's go with 10. I don't care about the step. Oh, it's doing t first, my bad. So we start at 0 seconds, and let's go till I don't know, 20 seconds, something like that. And -2 to 10. And the y doesn't matter. I've got it up at 2, so we'll just go from 0 to 4. See how I did? Cool. So it starts there at 3 and goes over. Let's see if I can get it to graph again. Window. Must still be going. No, done. Window and then hit graph. I didn't do it again. We changed a little something here. Let's make it from 0 to 10 seconds just so we can see it again. Starts at 3 right here, goes all the way down to -1 and comes back. I can quite assure you that takes some practice. It's been a little while of me playing with it before I finally feel comfortable enough to describe it. So that's the major application of derivatives. That's why Newton was actually working on derivatives, but then it pops up everywhere. Derivatives is an indication of sensitivity to change because sensitivity could be called slope. So for example, take the derivative of this sucker with respect to p, and you get 2 minus 2p. You graph it on a simple coordinate plane. And you get, starting up here at 2 and down to over 1. And you could say at b equals 1, the derivative is 0. It's not very sensitive. You could say here at p equals 0, it's up at 2. It's more sensitive. Notice we're no longer looking at slope. We're graphing the derivative. So don't get hung up on that at all. But it's just to give you an idea for things like marginal cost and marginal revenues. In business, they take derivatives all the time to say what's the marginal change. And that means a lot because you're making things, you're making tons of money. You think, well, let's just make more. Well, it might be more expensive to make them at the margin, way out there. You've made 10,000 of these things, and does it make sense to make 10,001? And quite often it doesn't. So you have marginal costs, just the derivative. Marginal revenue is right there. So how much does it cost to make the 10th widget? What the heck's a widget? That's a classic name for something that we don't care, just something we're making. Although the internet has appropriated that name, and it means something very specific on the internet after my looking up time. So it costs us $195. We're going to call it dollars per widget to make it. But hey, don't worry, we're going to sell it for $252. However, if you were in business and you were looking at this and you were saying, wow, my revenue's coming down for each one, my cost is going up for each one, and here we are at 10. Right now it still makes sense. There's 195 and there's 252. So hey, everything's good. We can still make it. We're still making money, but better watch out what the curve's doing. I don't know if this is accurate or not. As a matter of fact, I know it's not accurate, but you have to be aware of it. As you move along, things will change. So tell you right now, I haven't been to business school. Very, very rare you use calculus in business school. A lot of people there haven't taken calculus, but it's helpful. If you understand marginal changes, you really are a step ahead of everybody else. So that's it for now. Sorry for the super long video. A lot to cover. Happy mathing.